So, we will now look into the linear combination of vectors. This is very important. Let S be a vector space over R, say some Rn. Let P1, P2 so on Pm be vectors in S. Then for some scalar belonging to R, the linear combination X, which is C1 P1, C2 P2, some Cm Pm is in S. So, we can imagine that this set of vectors P psi are basically building blocks over which other vectors can be obtained. So, we can sort of imagine them to be as building blocks over which other vectors can be obtained, and basically your C1, C2 so on till Cm can be regarded as the coordinates for X over this set. No different from our notion of, for example, if you think about in 2-dimensional space, if you think about it as 2i plus 3j, right. If you think about it as 2i plus 3j, that means in I direction you are going 2 steps, and in the j direction you are going 3 steps. It is basically a position vector 2i plus 3j, right. So, your I and j you can think about them as P1 and P2, and your 2 and 3 are basically coordinates. Clear? So, though we think about this in terms of vectors, of course, we have to always have this in our mind that somehow our objective should be to take a signal and get this in the form of a coordinate representation. That is our objective, and this is the aim of this module. Well, we have to give an underscore for all these vectors following our convention, and often I miss this. Now, let us start with some definitions here. Let S be a vector space over R some m. Let T be part of this space, and you can imagine T can have infinite elements, right. T can have possibly infinite elements. A point x belonging to S is set to be a linear combination of points in T if there exists a finite set of points P1, P2 so on till Pm in T and a finite set of scalars C1, C2 so on till Cm in R such that this vector x can be written in this form. So, we will see some examples. Suppose I choose P1 and P2 in R3. Suppose I say P1 is 1 0 1 transpose and P2 is basically 1 1 0 transpose, and I form X to be C1 P1 plus C2 P2, right. I take X to be a linear combination of P1 and P2. C1 and C2 are basically scalars over the real, right. And if I just did this, I will end up with basically, now I take C1 times P1 plus C2 times P2. So, the first coordinate is what? C1 plus C2, next coordinate is C2, next coordinate is C1. Now, can you formulate can X, say suppose it is given as 5, 2 and 6, be formed from P1 and P2? Obviously not, right. You want C1 plus C2 to be 5, C2 is 2 and C1 is 6. It is not, right. You cannot think about this as basically a linear combination. So, therefore, you really cannot think about having any vector using a linear combination of these vectors. It is very very important to think about, because in signals also we can think about analogously, can we represent this signal belonging to this space as some linear combinations of some signals in the set. I have not gotten into the basis and dimension yet, but here is a feel, an intuition as you start scribbling through your notes to think through if such a thing is possible or not, and that is the whole idea about signal representation, right. I mean we will get to that point, but I think you should get a feel for this intuition. Now, at this stage, since most of you are graduate students, you have to go a little more deeper, asking more basic questions. If you were in high school, you would just imagine thinking about, yeah, my teacher taught me coordinate geometry, so therefore I am writing all these in a Cartesian plane and I trust what these results are true. But again, if you were to at this stage pose this question, what is the rationale behind construction of this coordinate axis in this particular way? Can I do it differently? Is my representation unique? So, these are very basic questions. If you ask these questions, you will really go back to your high school and revisit that what you did was indeed right and there is a theory behind what you were doing, right. So, let us ask this set of questions. is the representation of a vector as a linear combination of other vectors unique. What is the smallest set of vectors that can be used to synthesize any vector in S? We want the smallest set of vectors. The collection of vectors should be the cardinality of that set should be very small. What is the smallest set of vectors that can be used to synthesize any vector in S? Given the set of vectors P1, P2 so on till Pm, how are the coefficients C1, C2 so on till Cm found to represent X? Right, this is a basic question. If you were to think about it, if you know the answer, probably you will rattle it off. But if you did not know the answer, I give you this vector X and I give you this set of vectors P1, P2, P3 so on till Pm. How can I get this C1, C2 from this? Right? Techniques for doing that. Suppose X cannot be exactly represented by Pi. What is the best approximation? These are basic questions. I want to represent, let us say my set of polynomials is 1 t and t square. This is a set. Let's say the polynomials up to degree 2 is 1 t and t square. They form, these are the maximum polynomials up to degree 2, right. If I use monomials 1 t square is what I have. But I want some signal t power 5th root of t power 1 by 5. I want that to be represented using 1 t and t square, some linear combination of this. How can I do that? Some curve I want to approximate with something else. What is the mode? How can I do that? What is the best approximation? In what sense? So these are basic questions which one has to ask, right. That automatically leads us into this representation in geometric sense and the field of geometry of these vectors and is what we have to get. So we will try to address some of these questions. So but before we get into the details, we should now define what is linear independence. This is where we are. We just started with linear combination of some vectors and we said that it is sometimes not possible to express any vector as a linear combination. We may be restricted, but if I wanted to express it as a linear combination of these vectors, when can I do so? So these are questions which we have to ask. That gives us an idea into an important concept called linear independence. So let us see what this is. Let S be a vector space and let T be a subset of S. The set T is linearly independent if for each finite non-empty subset of T, say P1, P2 so on till P sub m, if for each finite non-empty subset of T, say P1, P2 so on till Pm, the only set of scalars satisfying the equation C1 P1 plus C2 P2 plus so on and so forth till Cm Pm, this is equal to 0, is the trivial solution So that means if we find Ci's that are all not 0 such that sigma Ci Pi is 0, then this set Pi I equals 1 to m, they form a linearly dependent set. In other words, if we find Ci's that are all not 0, I mean it is a very important step. Some can be 0, but some cannot, some can, even if I give you one element which is non-zero, then it breaks. That are all not 0, very important, such that sigma I equals 1 to m C sub I P sub I, if this is equal to 0, sometimes with a slight abuse of notation you may omit this bar for 0, I mean you have to imagine that it is a 0 vector. So there is a difference between a 0 scalar and a 0 vector, here it is a 0 vector, okay. So sometimes I may miss this underscore, but you may have to just register in your mind that it is a vector. Then this P sub I equals 1 to m, they form a linearly dependent set. So we will just take some examples and just cross check this. Suppose I give you P1 equals 2 minus 3 4 transpose, P2 is minus 1 minus 1 6 2 transpose, and P3 is say 1 6 2 transpose. are they linearly dependent? So, I'll also give you the answer. If you did 4p1 plus 5p2 plus 3p3, you get this null vector. So just cross check and then conclude that they are basically linearly dependent. Well, I think with this 4p1, 5p2 and 3p3, this might not be the case. They may not be linearly dependent. So let us just fix this up. So I think a negative sign here on the third coordinate of p2 and p3 completely negated would make this work. I mean, you can just quickly verify. This is 4 times 2, which is 8. This is 5 times minus 1, which is minus 5, 8 minus 5, which is 3, and 3 minus 3 is 0, and you can verify this for the rest of the coordinates, that if we change p2 and p3 in this form, and this satisfies this equation, and they are linearly dependent. So we'll see a few more definitions. Let T be a set of vectors in a vector space S over a set of scalars R. The set of vectors V that can be reached by all possible, I would say finite here, by all possible finite linear combinations of vectors in T is called the span of the vectors. So let T be a set of vectors in a vector space S over a set of scalars R. The set of vectors V that can be reached by all possible linear combinations of vectors in T is called the span of the vectors. So V is basically the span of T. Which means for any x belonging to V, there exists some Ci's belonging to R such that x is written down in this form . Now, we have a small note here. If V equals span of T, so this is basically the smallest subspace of S containing T. Okay. Now we have some definitions on spanning set. So, but before we get into the definition, let us take an example. Let P1 be this vector 1 1 0 transpose, and P2 is this vector 0 1 0 transpose in R cube. So, let us say X is C1 P1 plus C2 P2, which is basically C1 plus C2, and the last element is basically 0. So, V is basically the span of these two vectors P1 P2, and this is a subset of the space R3. Now, just imagine what is happening here, right? I mean, we take a linear combination of P1 and P2. The third coordinate is basically a null, and all we have is basically a plane, a two dimensional plane, right? I have C1, I have C1 plus C2. These two combinations will basically define this plane in two dimensions. So, that is what this is, and it is basically the plane where 1 1 0 and 0 1 0 lie, right. So, this is basically the idea. So, we have one more definition here. Let T be a set of vectors in a vector space S. Let V be a subset of S, and let us denote this, and we call this as a subspace actually, to be very precise. If every vector X belonging to V can be written as a linear combination of vectors in T, then T is a spanning set of the space V. This is an important definition as well. Now, we will end this with an example. Suppose I give you vectors P1, say 1 6 5 transpose, some P2 is -2 4 2 transpose, P3 is 1 1 0 transpose, P4 is 7 5 2 transpose. They form a spanning set of R3, and you can think, if you can just verify, -4 P1 plus 5 P2 minus 21 P3 plus 5 P4 is 0. And the set P1, P2, P3 are linearly independent, span R3, right. So, though we have these set of vectors P1, P2, P3 and P4, they are linearly related as per this equation minus 4 P1 plus 5 P2 minus 21 P3 plus 5 P4 is 0, and set T which is P1, P2, P3, they are linearly independent and they span this 3-dimensional space. So, this is basically a spanning set. Now, I think the important notion that we have is linear independence is an important concept, and linear independence provides us with what we need, a unique representation as a linear combination of vectors. That means given some vector, I can express this vector as a linear combination of some vectors, and the question is how to get vectors that are linearly independent and span the space, right, because I want this to span this space and I want these vectors to be linearly independent. So, this is the next notion that leads us automatically into the notion of basis of this, and with this notion of the definition of basis, which is basically a set of vectors that are linearly independent and that can span the space, now I can construct the space I want. It can be a vector space, it possibly can be a signal space. If it's vector, its base is vectors, in signals this is the basis for this signal set, right, and we will get to this in the next lecture.